everybody's still feeling pretty fresh, right? Like, it's just like, it's gonna be, I hope everybody liked Rob's talk, because this is gonna build a lot on the stuff that he talked about. So my name is Greg Pfeil. I work at a company in Boulder, a startup called Slam Data, and we do analytics for NoSQL stores like Mongo, Spark, things like that. So it basically is a large part of the system we write is a big compiler. And so the techniques that Rob talked about, and I'm going to talk about, are very useful in compilers, although they're useful in other places as well. But we needed them so much that we wrote this library called Matryoshka to give us these tools for doing the recursive stuff that Rob kind of talked about building up on your own. And this will be the more generic, even more generic than Rob's talk, about how to use these things yeah. So the library is there, and then also that second link is these slides. These slides aren't actually there yet, but slides from other talks on this topic I've given are up there already. So you can look at that. So Rob mentioned fixed point operators, right? Fix and co-free. It's weird not being able to see the screen myself. And so fix, as he mentioned, was this kind of recursive thing, whereas co-free is the same thing with an annotation at each node. And so you have these two things. Are these both fixed point operators? You have, the fixed thing has they both have the recursion in them. But is co-free a fixed point operator in the same way that fix is? Right, so we have this structure, and it turns out that we can do the same trick that Rob did with prof by extracting the type parameter and turning it into a functor. We can do that same trick with co-free. Co-free already has some parameters. We just add another one called b, and so we replace the recursive reference to co-free with b, and now we have this co-free f that has a head a and a tail with b, and just like we did with prof. You can, so this type, this functor type, has a name called empty, the environment comonad transformer, but it's called empty, and you can see the types match up, just has different names for the parameters here. And there's an isomorphism between the co-free and the fixed point, right, of this pattern functor, this environment transformer. So basically, in terms of actual fixed point operators, there's very few. Fix is the easiest one to reason about. There's also mu and nu, which I won't really talk about here, but they only do recursion, right? If they're doing anything else, you can basically extract that into another pattern functor. And in the case of empty, your original functor that you thought was your pattern functor is just embedded in that new functor. So you have kind of this more complex functor to deal with. So you have this isomorphism between these types, and we'll talk more about like why that's important or when you need to deal with that idea. But anyway, as I said, we can break down basically any recursive type the same way that prof was broken down from being recursive, even things like co-free and free. So Rob ended his talk with this unfold, unfold CM, which takes a single value and applies some function to it, and then gets this co-free structure. And sure, that's pretty generic, right? Rob talked about how unfold C is part of Scala Z, and that this function should be in Scala Z. It shouldn't be in Scala Z though, because it's just we'll see how we get to this point. But we'll talk about how to basically get to this point without having to write it yourself or have Scala Z add it. So to get to that, we need a little bit of terminology. The functions that look like this, which are, you kind of have to squint sometimes. There's a lot of different shapes that are close to each other, but not exactly the same. This is called a coalgebra. And you can see it's here. This coalgebra goes from some value to a functor containing that value, which is basically breaking that value apart. Right? You start with some a, and then you break it into multiple pieces. At least this is one way to think about it. You put those pieces into the functor, and then you recursively break down those pieces, and you expand it out into this recursive structure from some seed value. And the dual of that, which is basically, Rob kind of mentioned duals, you reverse the arrows on things, right? And that's exactly what you do here. Is you have an algebra, which is you start with some recursive structure. You start with some functor containing elements of whatever type, and then you combine them in some way so you only have a value of that type. So you might have a list of ints, right? That's an f of a, and you can just sum them together, and then you get an a out of that. So that's an algebra. So any function of that type is an algebra. You can see in Rob's case, the coalgebra is a little bit more complicated. It has a monad on there, but we have Kleisli coalgebras as well that do that. There's a lot of different shapes, again. Now, these algebras are used in folds and unfolds. Algebras are used in folds, coalgebras are used in unfolds. A fold takes the recursive structure and applies the algebra recursively at each level, folding it until you get that final single value, right? The unfold does the opposite, and this is what Rob was doing in his thing, where he started with the ID, pulled out a professor with all the IDs of its children, then recursively called the function on that, pulling out all those professors with the IDs of their children, and recursively until you bottom out and hit where there's no things left. And so usually you get an unfold by well, basically always. So in an unfold here, we go from, here's the A, to basically our fix of F. And as I said, these things have slightly different shapes. You can think of this cofree as with that pattern functor that I mentioned, the fix of N of T. And it, again, has a monad on it. And so this is the main fold, or main unfold function, and it takes the algebra that is applied to recursively. So these two things fit together like this. Folds take algebras, unfolds take coalgebras, and apply them recursively over some structure. So the simplest, so to get to this unfold CM that Rob was talking about, we'll start with the simplest kind of unfold, which is called an anamorphism. An anamorphism is this one down here. You can see it has a similar structure to Rob's, to the unfold CM. So whereas this takes an algebra, so given a function that basically expands one level of A to F of A, it gives you back a function that takes an A and returns a whole structure, right? So it's really a function transformation from this single level algebra to a full tree unfold. And so anamorphism is the same way as that, except it doesn't have the monads in it, doesn't have cofree in it. It simply takes a basic algebra, or coalgebra, sorry, and turns it into a basic unfold. And so that's, this is how these things work. They basically turn these single level operations into whole tree operations. And we can look at the implementation here. So this is psi, the Greek letter. For some reason, phi is used for folds, and psi is used for unfolds in all the literature for whatever reason. I actually like it because there's a bit of a mnemonic, I think, whereas, I don't have the fold here, but anyway, they have a very similar structure, phi and psi. The psi looks like it's opening up, like it's expanding things, whereas the phi looks the same except it's closed. It's like a closed circle. So it's more like bringing things together as folding and then the unfolding of the psi. Maybe that's where it came from, but I didn't see any mention of the mnemonic in the literature. So anyway, I tend to use it for those same things, the unfold and the fold. So here we apply this coalgebra to your initial value, right? So you get some F of A, and then you map over that, get it for each A, applying ana directly to that, and so then you expand each of those recursively. And you just go through the whole structure, so it's pretty simple walking through the whole thing. But again, we're not yet at unfold CM. So, so here's a simple example of an anamorphism. We have a two-component sum type here, right? There's expressions that are represented by either literal numbers, just an integer, or a multiplication of some A, right? So with the fixed point type, you would have like multiplication of num2 and num4 or something like that. And then there's an unfold here, right? This is that same type, A to F of A, right? Int to expr of int. And this basically is this, not fully implemented, obviously, but it basically says if the I is prime, just return the literal number. Otherwise, break that number down in some way. So I get like a mole of 2 integers. And then again, we can recursively apply this using anamorphism to get those, to get that all the way down to have a full fix of expr expression. So if you were to call this anamorphism, given this this coalgebra on the number 48, you can think of it something like this, just kind of shorthand for this math shorthand, where you can, every step it would just kind of extract 2, extract 2, extract 2, extract 2, until all the numbers are prime, so you've prime factored this number now. Now, if you actually apply that, you end up doing, this is how your recursive calls actually end up happening. You call 48, it splits out 2 and 24. When it recursively calls the same function on the int 2, all it can do, since it's prime, is wrap it in a literal number. The 24, when it calls recursively on that branch, it can apply the same multiplication, splits down to 2 and 12. Again, the 2 terminates, 2 and 6, 2 and 3, and then they both terminate at this point. So now you have your whole recursive structure, which looks like this with those fixed point constructors that Rob was talking about. Again, if you remove just fix from all this, you get what you would normally think of as a directly recursive data structure. And I know the fixed stuff is ugly. You don't tend to see it very often in code you write. You tend to see it in like examples and tests, which is bad for talks, but when you're writing things, you tend to, because you're working with these algebras, you tend to work one level at a time. Occasionally you have 2 levels or something like that, but the noise of this doesn't actually show up very much when you're working with it. So from an anamorphism, that's the most basic fold, or unfold, we can do a Kleisli version of that, a monadic version, and we get ana m. And it's basically the same thing. This adds the m that we had seen in unfold CM, right? And maps turn into flat maps, maps turn into traverse, and you have some flat maps and mappings in there. But it's doing this exact same thing, just propagating the monad through appropriately. And so that gives us the monadic part of that unfold CM. And the last piece we need, though, is that unfold CM is giving us a cofree at the end, whereas ana m gives us a fix. Right, so we need that cofree. So this is what's called an algebra transformation, which takes one algebra, or in this case coalgebra, but takes a coalgebra and returns a new coalgebra. In this case, it's taking an algebra for an arbitrary f and turning it into one for the n of t. And what it basically does is it annotates each node with the seed value that was given for that node. So you see you get some seed value in here, and you pair that seed value with the result of unfolding the rest of the tree. So this builds up that cofree structure from the seed value. And so, so now you can redefine unfold CM using ana m and attribute coalgebra m. So then, so you have this exact same fold, but you now are basically just composing these structures here. And there's a lot of different ways to transform algebras and things like that, and we'll talk in a little bit about why you want to do different, or why you want to basically pull that stuff out of your functions and not keep it in your functions. Just to cover a little bit more ground first. So we went over the unfolds. The dual of these was the folds that I mentioned before. The simplest case of that is a catamorphism, which again, you can kind of see how it's all just the reverse of the previous, right? So instead of going from A to fix, we go from fix to A. And instead of the algebra or the coalgebra, you're gonna have an algebra to handle that for you. And you can see here that in the case of ana, we first call the coalgebra and then recursively apply ana to the result of calling the coalgebra. With a catamorphism, we first recursively call kata and then call the algebra on the result of the kata. So the idea being there that with an anamorphism, you start at the root, basically start at this whole structure you have, and are basically building things top down, right? You build the outermost layer first, then the inner. Whereas with a catamorphism, you first traverse to all the leaves, and then you fold those leaves, and fold the things that had those leaves, and fold until you get back to the top, some core value. So they work in different parts of the traversal of the data structure. So here's a simple, on that same expr where we had a num and a mul node, here's the evaluator for that, very simple evaluator. It just multiplies the numbers together. If you get a num, it's the literal num. Otherwise, you multiply the two values. So this is this very simple algebra. And in this case, we apply it to that result we had gotten before from breaking apart 48 to factoring out to its primes. Again, we just apply a catamorphism to the eval. We get back 48 as a result. And so it's just folded that all down. And this is, the catamorphism is a generalization of fold right, reduce, or any of those kind of folds you're used to. They can all be written in using kata. So I mentioned before that ana starts with some value a, does all of its work, right? As it calls the thing as it goes recursively. And on the way back, all it does is wrap each result in the fixed point value. And then catamorphism first extracts each functor from its thing, and then as it goes to the leaves, and as it folds back down, it applies the algebra at that point. So if you want to do something like, you have some value you want to apply and unfold to it, and then apply a fold to it, you end up traversing your data structure multiple times. But one of the big benefits of this approach to breaking things down to work at a level on one level at a time is you get nice optimizations of these things. So if instead of doing a anamorphism followed by a catamorphism, you actually call high-low morphism, which takes both the coalgebra and algebra, it can interleave those calls. So basically, as you go to the leaves, as you're expanding out the thing, it calls the coalgebra on it, and then it applies the algebra on it as you go back to the root. And so now instead of doing multiple traversals and creating this intermediate data structure here that's that's like this tree, you can actually avoid ever creating the tree. You've never created this fix of f, right? You've never created your recursive data structure. It doesn't exist in memory at any point. So you basically have this great optimization of not doing multiple traversals and also just not building up those intermediate structures along the way. And so there's lots of, so this is called fusion, right? Because, versus regular composition, what fusion does is it eliminates intermediate data structures like that. And that's getting that kind of efficiency gain from composition is like, it's great. And there's lots of ways that using recursion schemes, you can do that. One of the other ways is what's called a zygomorphism. In this case, you have multiple algebras. So here's a single algebra, right? It's some language, a lambda calculus, annotated, or not annotated with types, but a fold that looks at the types, and then based on the types of some node, figures out the type of this node. And so with this, we can do with a nice, as I did before, I did the attribute coalgebra to go from the fixed to the co-free. This is the same thing. So just starting from the single algebra that says, given the types of all of my children at whatever node I am, I can get the type of myself. This then builds up a whole co-free structure using the attribute algebra transformation, so that you don't have to do any thinking when you're writing your inference algorithm, saying like, okay, well I have to keep this stuff around and do all this stuff here. You can basically do that after the fact. You write the simplest algebra possible, and then you can turn that algebra into something that does what you want in specific cases, and you can transform it differently in different places in your code. In this case, we say like, oh, well, we want to have the whole tree annotated with the types at the whole thing, as one of the examples that Rob mentioned. And so that's exactly what this does. But there, again, we have fusion in various cases. If you're building up a structure that has these types annotated everywhere, you're probably doing something later down the line that uses these types for some reason, right? Like figures out if things type check or like just validates whatever. And so if you have another algebra that is basically like operating on some value and the type of that value to determine like what should be the result, you can actually use what's called a zygomorphism that combines two algebras together, where it basically uses the first algebra, figures out the types, and then gives you that type as a little, basically as an annotation just on that one result when you're calculating the value. So this is another case where you get fusion. You never actually build up the intermediate co-free structure. Just at each node, you say like, oh, call this one first, and then give me the results of that to use when I call the next algebra. And so again, you end up doing only one pass over your data. And there's so many different ways to combine these things together. Another one is zip. You have two algebras that calculate different things over the same kind of structure. Right? You can zip these two algebras together. And so now instead of having an algebra from expr string to string and expr int to int, you have a single algebra that's expr string and int to string and int. And so now even though you're calculating completely unrelated stuff, you can do one pass over the data structure and get all the results at once, rather than doing them each in parallel. So there's lots of ways, again, to combine these things and get fusion and stuff like that. These things generalize. There's tons of different things here. So this is my cheat sheet that I keep on my desk all the time. Although I use it a lot less now than I used to. But there's tons of these things. They all have various relationships to each other. This is actually only a subset, although it's the most common subset. And it turns out, though, that all these things, almost all of them, are special cases of these generalized forms, G cata and G ana, which operate over either a comonad or a monad. I'm actually going to not get too into, well, yeah, just as a, yeah, I'm not going to get into this part. But you can define any of the normal folds like cata or the zygote we just talked about just by specializing these G cata or G ana operations. And it turns out, just like you can generalize those, you can generalize the hylomorphism, being the one that combined the multiple passes into one, right? So you get a G hylo, and in fact, with the G hylo, the generalized hylomorphism, you can get both G cata and G ana, so you don't even need those. You can just have the one G hylo, and then get all of your folds and unfolds from the one operation. Although we tend to implement more of them as needed, just for efficiency purposes in implementation. So when you've written something in this style and you have all these functors and you're dealing with these fixed points, one of the nice things you get is now you have all of these operations that work over any tree structure. Here's just, I mean, a couple, but we have a library of algebras that are just available to us no matter what kind of structure we have. To get the size, like all the count of all the nodes basically is the size, the height of the tree of your data structure, convert to an actual rows tree using the Scala tree. Which can be useful for like showing these things to actually print out like a draw tree structure instead of just trying to like print or write custom shows for everything. Yeah, so anyway, there's tons of these things you just get for free as a result of having all this. So here is a case, just to show this is something we actually use. This is kind of stripped down, but the idea here is we have 4 distinct algebras. They're actually 4 very different kinds of things. The first one is what's actually called a transformation. It's neither a fold or an unfold, but very related to the two. The second one is an unfold. The third one is a fold, and the fourth one is a fold. But they have different, like, you can see that these two cases can error. So this is an unfold that can error, this is a fold that can error. And anyway, they have different behaviors, all of them. And so the thing is that the nice thing about this, this looks complicated. This is where we put them together, right? This is, oops, that is pretty complicated. But all that code is doing is making the types line up. Like, it's not doing any thinking about anything. It's just making the types line up. So the benefit of that is that these folds are all very simple. None of them have to worry about how they interact with any other part of the code, right? We basically write them in the most direct way possible, or these algebras and coalgebras. We write them in the most direct way possible, and then only when we put them together do we think about, like, how do we have to change the types of them or do things like that in order to make them all fit together. Like you can see here, we zip 2 of them together. So we get, and this is also like, this one gets lifted into a monad because it doesn't have the error monad, but the other one it's being zipped with does, so we have to lift it into the monad, generalize it along one of the dimensions, like I mentioned that G cata, like that. Then it zips them together. These two now have the same shape. This identify synthetics and infer prov, and so we can zip those 2 together, and then we say we don't just want to have those, we want to actually annotate the whole tree with those, so the attribute algebra. But then, as I mentioned, you don't actually have to build up that intermediate structure when you're if you want to like use those values later. So then we combine it with this other operation that uses those annotations, and so in one pass we've done like all this multiple things and just get the result we want in the end, basically. Yeah, and so anyway, we have dozens of these algebras all over our code. Many of them, some of them don't, but again, it's nice to just write the code without thinking about any external complexities, right? You just write your algebra only thinking about the logic of that piece of the thing and not how it has to fit with anything else. But many times we actually do use these in different situations where we have to either, like lift them into different monads or zip them up or attribute them or not attribute them, all depending on what context they're being used in. And on what functors, because like with before I showed those, there are various, there's like a whole bunch of these things that can be just applied to any functor since we've used it, since we've written things in this fixed point style. So this is kind of an overview of a quarter of what exists right now. And I want to talk a little bit about like the stuff we want to do going forward briefly. But the first thing, one of the things we wanted to get done was Scala.js support, but Edmund did that for me, so that was nice. So that's no longer a future direction, that is done. And pretty easy. Well, I wouldn't say easy. I mean, the code looked simple, the changes, so that was nice. We want to get to library independence. Right now, we're very strongly coupled to Scala Z, and I like to break things apart so we can, people who use cats can use it, people who use Scala Z can still use it, people who don't use either can take advantage of it without pulling in extra dependencies. The library actually, as I mentioned before, there's that isomorphism between like co-free and env, and there's also one between free and another pattern functor, and various other, and list has a pattern functor you can pull out of that, because normally you think of list as being a recursive data structure. There's basically a whole library of things that are in the standard library or Scala Z or whatever that are recursive that Matryoshka has basically defined fixed point versions of with. They're still a little, they're not as rich as they could be, but they could be fleshed out to be like equivalent, like with all the right instances and everything like that that the standard ones have. So anyway, if people want to use those directly, that should be available. Currently working to try to use Daniel's shims library to make those pieces, to tear those pieces apart without destroying the whole library. So yeah, I've made some progress with that. Another thing is directly recursive types. So I mentioned before that we have this distinction between, or there's an equivalence between co-free and this fixed point of the env functor. The problem is right now is whenever you need one of them and you have the other, you need to transform your whole data structure. Matryoshka helps a bit. We have isomorphisms that basically work. So if you have a fold, you would like to write, co-free, have some co-free value, and you'd like to fold it down using your algebra and get your A back. The problem is your algebra is based on this env functor, this pattern functor of the co-algebra, or sorry, of the co-free. And so before you can apply that algebra, you first have to convert the structure. But since it's implemented as a co-algebra, this conversion between the two, you can use a hylomorphism and convert the structure as you go and then apply the fold. And the same in the opposite direction. You want to do an unfold on your co-algebra to a co-free. But again, your unfold is defined in terms of env, and so you have to unfold to env and then apply the conversion from env back to co-free. So it's not terrible. Like right now you can do this and it works in such a way that like it's fairly efficient. But there are ways to generalize, and like as I mentioned before, there's pattern functors for all these recursive types, list, co-free, free. And the simple case is fix, where the pattern functor is just the functor itself, but in list, the pattern functor is an A, and then the recursive thing, env, and then the recursive thing, co-mt, and then the recursive thing. So what we really want to do is modify the way the recursive definitions work, which has been complicated because of Scala's limited type family-ish stuff. It has associated types, which help a bit, but I've run into a bunch of problems along the way. But the idea is that instead of just saying that you have a fixed point and it has a functor, you can define, so this is the type class. How we actually define things like catamorphism is done inside this type class. And normally there's a function that you have to implement called project, which takes your fixed point and unwraps one level of it. Right? And that's used to implement all these other things. It's project. In fix, it's called unfix. What we have to do is change that so your fixed point type is actually a proper type, not a crazy shape type. And then you have to define a functor in the type class that says this is the functor for this fix. So for fix, it's easy. Fix of some f, the functor is just that f. The base, the pattern functor, is just whatever that f is. For free, you have some free of f of a. In this case, the pattern functor is not just f, it's this co-env, which as Rob mentioned, the only distinction between, or the distinction between free and co-free is the having both or having one or the other. So this co-env is a lot like env, but instead of having both, it has one or the other. But in this case, here's the function you need whenever you unwrap one layer of the structure. So anyway, there's been problems actually implementing that. Another thing that actually does work is mutual recursive types. So right now, all these recursive structures have to use the same set of nodes all the way through them, right? But it's not uncommon to Yeah, it's not uncommon to have recursive things that, like, when you're doing a programming language, you have a distinction between statements and expressions. And statements can have expressions inside them, and expressions can have statements inside them. And so they need to refer to each other, but you don't just want to have like one thing that says like, oh yeah, put whatever wherever, and we'll like later do stuff to like figure out if we put things in the right place and like make all your other code more complicated. Which is, if you have something like this, there's some language that has int literals, pairs, and a few operations on those structures. That's basically what you have, is everything can go anywhere. But it would be nice if you could actually constrain this to say like, well, the only thing you can put in molt is things that are actually, would evaluate to the type int, and you can only call first on something that's a pair, and stuff like that. So you want to be able to restrict which parts of this type can appear in which places. And we can do that. We basically have a more complicated version of functors, higher order functors, that give us this ability to add an extra type parameter. And so the extra type parameter basically gives us that constraint. So here we can say like add takes two of these things that qualify as int typed nodes, and return, and it itself is always an int type node. First takes something that's a pair type node, right, and returns something that's whatever type the first half of that pair type node was. So if there was an int there, then it's an int. If there was another pair there, then it's going to return another pair as the type of its thing. And so basically in this case, not in all cases, but in this particularly simple case, it's basically acting as a type checker on the structure itself. So you can never build an ill-typed data structure. With real type systems, you couldn't actually do that. But there are other, like I mentioned with statements and expressions, there are distinctions that are expressible this way that are very useful to put into your data structure. And then there's adjoint folds, which, as I mentioned before, these things are all generalizable to basically like one G high-low thing. But it turns out there's a whole bunch of other ones, including, for example, this one over on the side, this mutumorphism, that does not fit in this pattern of all these main ones in the middle. And there's a whole bunch of other ones too that deal with structural recursion and other things. But if we generalize the whole thing to not deal with comonads and monads, but to deal instead with adjunctions, then we get all the ones we already have, plus a whole class of other ones that aren't yet supported. I didn't really have anything that I could fit on a screen that would show anything about that. But that's everything. We have a Gitter channel. I love if people just ask any questions about anything there. And that's me. So that's it.